So hi, I'm Noah, and I'm going to be talking today about the hardness of average-case K-sum. This is joint work with Zvika, Brakerski, and Vinod, Vaikuntanathan. Okay, so let me tell you what K-sum is. So K-sum, the input, it's a computational problem. The input is A1 through AM. These are elements in ZQ, so they're integers modulo Q. And the goal is to find a subset of K of them, K distinct indices, I1 through IK, such that AI1 plus all the way up to AIK equals 0 mod Q. So in other words, you want to find a subset of K of the elements that sum to 0. So let's get our bearings. Let's think about sort of the optimal some algorithms for this problem. So the most naive algorithm is a brute force search, which runs in time m to the k, right? So, I should mention that I'm thinking of m and q as going to infinity and k as the constant right now. There's an m to the k time algorithm that just enumerates all possible k tuples of the input m elements. There are m choose k of them, which is about m to the k. And just checks if they sum to 0 or not. It turns out that you can do a little better. In particular, there's a meet in the middle algorithm that runs in m to the k over 2 times. And that works by enumerating all k over 2 tuples instead of enumerating over all k tuples, and then sort of matching pairs of k over 2 tuples that happen to sum to 0. And it turns out that this m to the k-ish flavor of running time is tight. So this is a very active area of research. People are still trying to show that this m to the k over 2 is truly optimal. But at a super high level, if you don't care about the constant and the exponent, we already know that this is optimal. So in particular, this is an m to the omega k time lower bound due to Petroscu and Williams, assuming the exponential time hypothesis, which I'm willing to assume. There's also a dynamic programming or fast Fourier transform algorithm that runs in time Q. So remember, Q is the size of the group. And this is also known to be tight. In particular, there's a lower bound of Q to the 1 minus epsilon under SCTH due to Aboud et al. At a high level, we understand this problem pretty well in the worst case. There are sort of two regimes. There's the kind of sparse regime, where m is small. In particular, m is much, much less than q to the 1 over k. And there's a dense regime where m is large. M is much, much larger than q to the 1 over k. In the sparse regime, the right running time is like m to the order k. In the dense regime, the right running time is like q. But this is random. So I'm interested in the average case version of the problem. In particular, the average case version of the problem, it's the same thing, except I have this squiggly line here, A1 through AM squiggly line, ZQ, which means that A1 through AM are sampled uniformly at random from ZQ. That's what makes it an average case problem. And now I'm going to restrict my attention to the dense regime, to the case when M is much, much greater than Q to the 1 over K, because if M is not much greater than Q to the 1 over K, then this is an unfair problem, because with high probability, there simply won't be a solution. And it's no fair to ask to give someone a computational problem that doesn't have a solution. So we assume that M is at least Q to the 1 over K to make the problem interesting. So of course, the worst case algorithm still works in the average case. So there's still this order Q time, or roughly Q time algorithm that works for the average case problem. But it turns out, perhaps surprisingly, that there's a faster algorithm. There's a Q to the 1 over log K algorithm, which unfortunately doesn't have a real name because it's been discovered many times. So I've often heard it referred to as the BKW algorithm for Bloom, Kalai, and Wasserman, who published about it in 2003. It's also called Wagner's algorithm because Wagner published about it in 2002. Many other people published work on it. Sometimes it's called the generalized birthday algorithm. I'll actually show you the algorithm. But I think this is kind of surprising the first time you see it, because remember that in the worst case, we know that there's no sub Q time algorithm for this problem. There's no Q to the 1 minus epsilon time algorithm for this problem. But in the average case, there's actually a much faster algorithm. And this is like surprising because it means that, for example, the worst case for this problem is not a random instance. There are instances that are harder than random instances, which I don't know. I think that's interesting. So of course, I'm a theorist. I see an upper bound and I want to prove a lower bound. So my question is, can we show that there's no better algorithm up to constants in the exponent than BKW Wagner? Oh, and I should mention that BKW and Wagner, like, it only works in the regime where M itself is quite large. So the problem only makes sense when M is larger than Q to 1 over K. But for BKW Wagner, you need M to be even larger, Q to the 1 over log K. And you'll see why when I show you the algorithm. But like, actually in the average case, it often makes sense to just kind of imagine that instead of having a fixed M, just kind of imagine that the algorithm gets to choose M. Or if you like, the algorithm gets to press a button and it sees a sample AI. And then if it's not happy, it presses another button and sees another sample AI plus 1, et cetera. And it just eventually has to find some subset of K elements that it's seen that sum to 0. It turns out that that sort of on the fly version of this problem is more convenient to think about. So in that sense, the BKW Wagner algorithm is just a Q to the 1 over log K time algorithm. The fact that it needs Q to the 1 over log K samples is sort of baked into the sort of adaptive nature of how I'm describing the problem. Okay. So in order to tell you, of course, I'm going to prove this hardness result. That's why I'm giving this talk. So I'm going to prove that Q to the 1 over log K is optimal. And in order to tell you about that, it's going to help a lot to define this problem called short integer solutions, or SIS. And I'm kind of torn on how to present this because, like, in some sense, it's this beautiful problem. It's extremely well studied, and it has like a very rich history. On the other hand, like, for the purposes of this talk, it's really best to just think of it as n sum. So what do I mean by n sum? Well, I'm calling it n sum instead of k sum because the idea here is that whereas before I was thinking of k as a constant, now I'm thinking of n as going to infinity. So this is n sum for n going to infinity. And again, the input is uniformly random. So it's an average case problem, A1 through AM. And again, like, it sometimes helps to think of this as kind of adaptive, where we request as many samples as we want. They're from Z big Q. So big Q is going to be very large. In fact, I really kind of care, although you won't see why, about the asymptotics here. So I really care that Q is roughly n to the n. And the goal is essentially to find an n sum of the inputs that equals 0 mod Q, mod big Q. Actually, the problem, as typically defined, I wanted to give the right definition. So the right definition is actually a little friendlier than that. It's a little easier than that, in the sense that, like, you only need to find some linear combination of the inputs where the coefficients in the linear combination have L1 norm at most n. But okay, for our purposes, it helps to think of this as just n sum. And there's a theorem that goes all the way back to 1996. We actually use a theorem due to Jinx in 2016. But Itai's original theorem showed a worst case to average case reduction for this problem. So in other words, this is an average case problem by definition. The input's random. But Itai showed that this is as hard as some worst case problem on n-dimensional lattices. I'm not even going to tell you what it is. It's called SIVP. It's a very well studied problem, which is widely believed to be 2 to the order n hard. So this is a reduction from a worst case lattice problem to this average case version of n sum called SIS. And of course, like, for our purposes, this is like very exciting because, like, I want to prove like a fine-grained average case hardness result. And there's a problem that looks very similar to the problem that I want to prove an average case fine-grained hardness result that already has such a result. So it's like almost like our work is done for us. But I should note that, like, actually SIS in some sense is like very different from K sum. So in other words, when K is constant, the problem behaves very differently. In particular, like, the optimal algorithms for SIS are very different. They're sort of more geometric than the combinatorial algorithms that you use to solve K sum. it really is kind of a different problem, but obviously syntactically it looks very similar, which is why this is kind of exciting. So I think our goal is kind of obvious. So like we want to reduce SIS to average case k-sum. And we want the parameters to work out correctly. So like we want q to the 1 over log k hardness. We have 2 to the omega n hardness for SIS. So that means we want 2 to the n to be like q to the 1 over log k. So in other words, can we sort of bounce around in parameters? And just to like point out why this is like non-trivial, like obviously any k-sum is also a solution to SIS, but in the parameter regime that we care about SIS in, we don't expect there to be any solutions to the k-sum problem, right? We don't, Q is much too large, and M, if M is less than 2 to the order n, then M will be much too small for there to be any k-sum solution. Okay, so let me now tell you about the BKW algorithm, the Wagner algorithm for k-sum, because it turns out that our reduction is going to sort of borrow heavily from these ideas. Also, it's just beautiful, and you should see it at least once. So I'm going to assume for simplicity that k is a power of 2, so it's 2 to the L, and that q is p to the L for some integer p. This is just for simplicity, it's not necessary. And remember, like this algorithm works in the setting where m is at least q to the 1 over L, q to the 1 over log k, which means q to the 1 over L, which is p. So that's going to be important. And the idea here is to think of our input elements A as being written in base P as so, you know, B0 plus B1 times P, etc. And then what we're going to do is we're first going to find M over 2. We're going to sort of zero out the digits of our A's in base P one at a time. So the first thing we're going to do is find M over 2 disjoint pairs, I and J, such that AI plus AJ equals 0 mod P, not mod Q, but mod P. So this we can do quite efficiently. In particular, we can just like sort all the input AIs modulo P, and then just pair up AI with minus AI. And I'm claiming that we can find like M over 2 disjoint pairs. Obviously, we can't find more than M over 2 disjoint pairs, but because M is much, much larger than P, we expect that basically every A should have a friend, should have a minus A that it could be paired with. So we do expect to be able to find like M over 2 disjoint pairs, and we can do it in essentially linear time. In step 2, we apply the same thing to the pairs. So I look for disjoint 4 tuples, I1, J1, I2, J2, such that AI1, AJ2, AI2, AJ2 sums to 0 modulo P squared. And how do I do that? Well, now I have a bunch of pairs that sum to 0 mod P. So I just reduce those sums of all those pairs modulo P squared. I sort those sums and I do the same thing. I pair everything up. So again, I can do this in linear time. Again, because M is much, much larger than P, I can find essentially, like, I can essentially group every element into a 4 tuple. So I can find like essentially M over 4 disjoint 4 tuples. And then I'm just going to keep going. So I'm going to zero out. So I'm going to set things to 0 mod P, then 0 mod P squared. And finally, I'll get 2 to the L tuple in the Lth step, so a K tuple, that sums to 0 mod P to the L, which is Q. So in other words, I'll get a K sum, get a solution to the original K sum instance. So that's the algorithm. Really beautiful idea. Again, it's been sort of arrived at many times. So here's the idea behind our reduction, the sort of naive idea that doesn't quite work. I'm going to do kind of a similar thing. I'm going to take my N in my SIS instance, in my N sum instance, to be K to the L, and my Q to be Q to the L. My big Q to be little q to the L. And then the first step, I'm going to use my K-sum oracle to find many disjoint K tuples, I1 through IK, such that AI1 plus all the way up to AIK sums to 0 modulo Q. right? So this is what a k-sum oracle allows me to do. It allows me to look at my input AIs and find a subset of them, of k of them, that sums to 0 mod q. Now, the subtlety here is that I'm claiming that we can find m over k such disjoint k tuples. Clearly, I can find one with my oracle, but I'm claiming that we can find m over k of them. It turns out that that's kind of false, but I'll say more about that later. So let's pretend that's doable. And then I'm just going to repeat, right? So now I'm going to look at my k tuples, the sums of my k tuples, which sum to 0 mod q. I'm going to look at them modulo q squared. I'm going to find k tuples of my k tuples that sum to 0 mod q squared. And I'm claiming I can find m over k squared disjoint k squared tuples. I should say these exist. If you choose the parameters properly, there exists such k tuples. The question is, can we find them using our k-sum oracle? And of course, I keep going, and eventually I find a k to the L tuple, so an n tuple that sums to 0 mod q to the L, which is big Q. So in other words, I find a solution to my SIS or n sum instance. So it turns out that this reduction actually does work if my k-sum oracle is in the worst case. In particular, I was vague about how I'm going to find so many disjoint k tuples. If I have a worst case oracle, then that's not so hard. What do? Well, I call it on my m inputs. Then I set aside the k inputs the k elements that it output for me, and then I call it on the m minus k remaining inputs. I set aside the result. I call it on m minus 2k inputs, etc. And I do that until I'm essentially out of inputs. And that will work in the worst case. You can prove that will work. And that will give q to the order 1 over log k hardness of worst case k-sum. But of course, that's not interesting. We already know q to the 1 minus epsilon hardness for worst case k-sum. We want to prove this for average case. And for the average case, this doesn't work because our oracle could refuse to cooperate. Like if I take out a bunch of elements for my input, a bunch of k-sums for my input, my oracle might look at its new input and say, this isn't random anymore. It's missing lots of k-sums. Or even worse, because the oracle itself gets to choose which k-sums I take out, it could be the case that it preferentially takes out certain elements that it particularly likes, and then refuses to operate when it sees input that's depleted of such elements. There is a naive way to try to make this work in the average case, which would be, say, instead of starting out with m samples, to start out with m to the L samples, and then call my oracle on m to the L minus 1 disjoint subsets of size m, and then L to the m minus 2 disjoint subsets of size m, and then m to the L minus 3 disjoint subsets of size m, etc., until eventually I get one n tuple at the end. But this doesn't work. It requires you to start out with way too many samples. If you do the math, it requires you to start out with like n to the n over k samples, which is useless because we're trying to reduce from a problem that's only 2 to the order n hard. And if we need to generate n to the n over k samples to get started, then we certainly can't prove 2 to the order n hardness, or we can't use 2 to the order n hardness. Our solution, which I'm not going to say much about because I'm running out of time, is to convert m samples into capital M samples on the fly. So we figure out a way to, like, at any step of the algorithm, at any step of the reduction, expand the number of samples. So specifically, like if we start out with little m samples, we're gonna use this trick to generate m squared samples. Then we're gonna call our oracle on m disjoint collections of m squared samples. And now in the next step, I'll have m k tuples to work with. And I'll just do the same thing again to the sums of those k tuples. I'll expand them to m squared, call my oracle on disjoint things, and continue as like that. This is going to hurt us a little bit. Instead of finding k sums, we're actually going to find k squared sums, but that doesn't bother us so much because remember, our dependence is logarithmic on k. So this is going to cost us in the constant and the exponent, which barely matters to us at all. So that's the end of my talk, and I think I'm about out of time. In summary, we already kind of knew essentially tight bounds for worst case K-sum. We prove essentially tight bounds for average case K-sum in the dense regime. And we use this non-standard worst case fine grained hardness assumption, which is the hardness of lattice problems, which I personally think should be of interest more generally to the fine grained community. Particularly, like, we already knew this worst case to average case reduction for lattices. So we show that can be extended to K-sum, but it's natural to ask, like, what else we can apply this to. Okay, so I'm out of time. Thank you for your attention, and I'll be happy to answer any questions at the session.